So I won't go through too much of the theory since you guys have probably already seen it in lecture. We'll just go straight to examples and talk about things. So if we're given polar coordinates, they might look like, they basically look like regular Cartesian coordinates. So let's just look at this real quick, pi over 6. So polar coordinates, this is r, and this is theta. So I'm sure you guys have already seen, here's your r, and theta is this angle measured from this axis here. So now let's express, just as practice, let's express this, four equivalent coordinates. We'll do two positive coordinates and 2 negative coordinates. So again, this is as simple as, so if we keep the r as is, we can essentially rotate the angle. So if this is, let's say 3/2, and we rotate by pi over 6, which is roughly 30 degrees. So this is our point here, 3/2 pi over 6, based on what we're given. We want to try to find equivalent expressions for this. So we can simply rotate this 2 pi radians. So if we add 2 pi radians to that, we'll get 13 pi over 6, right? 12 pi over 6 is 2 pi radians. We can also subtract. We can also subtract 2 pi radians. So we're essentially going, oops, not that way, the other way, this way. So we're subtracting 2 pi radians. And if we do that, we'll get negative 11 pi over 6. And of course, we can do this, we can express this with a negative r. So what I meant here was positive r and negative r. So if we have a negative r, so we're basically saying we're going to come to the negative 3 pi over 2, or 3 over 2, right? So if we want to rotate this clockwise, this is positive angles. So for positive angles, we want to go, well, we want to go pi plus another pi over 6, right? So that would be, what would that be? 7 pi over 6. So if we had negative 3 over 2 for r, we would have to rotate this 7 pi over 6 to get it to this point here, right? So similarly, if we were to start with negative 3/2 and then now rotated it clockwise, this would be, I think I misspoke last time. Did I say anti-clockwise? So the first one was anti-clockwise. And then this time we're going to rotate it clockwise. So this would be negative angles. So we would have to rotate it negative 5 pi over 6 to get it to the point that we wanted to. So these are all equivalent to our original polar coordinate. Okay. Any questions on that? All right. So now let's try expressing polar coordinates in Cartesian coordinates. So if we're given 4 as our radius, 3 pi over 2 as our theta, our angle, let's represent this, express this in Cartesian. So this is our normal x and y. So essentially x is just r cosine theta, right? And y is r sine theta, right? So when we look at this, if we use polar coordinates to express this, we're going to have 4 and 3 pi over 2 is going to put us, it's going to put us pi over 2, so down here, right? And then this distance is 4, right? So now if we want to express this as x in Cartesian coordinates as terms of x and y, we would just plug into these two equations here. So this would be equal to 4 times cosine of 3 pi over 2. And this would be 4 sine of 3 pi over 2. And of course, this would be 0, and this should be negative 4, right? And it makes sense if we just look at this as x and y, right? This point is just 0, negative 4, right? So it works out. Okay, so let's write, so for the following, write polar coordinates between theta equals 1 to 2 pi. Okay. So this is all included in the worksheet that I just posted right before the discussion. So you can refer to that if you want. So we want to express this guy in polar coordinates. So this is in the form a plus bi, right? And I, where I is essentially the square root of -1, right? I'm sure you guys have seen that. This, and I don't mean divide by here. So this is in the form, write it in red, a plus bi, right? So when we draw our coordinate system, this is our real axis, and this is our imaginary axis, right? So our A represents our real number, so we're going to go -2, and our B with the sign represents our coordinate in the imaginary axis, so that would be 2 this way. So the intersection of those 2 points is there, right? Not here. So the distance from my origin to that point is my R. And now we want to express this as R comma theta. So this is polar. So theta would be this angle, or it could be this angle, right? But we'll just express it from counterclockwise from this real axis, from this point here. Okay, so the easiest way, there's a couple ways you can look at this. I personally just like to look at everything as a triangle, right triangle. So that's what I would view. But some people like to just put it into sines and cosines. So this point here, which is -2, remember, if we were to express this in Cartesian coordinate, it's r cosine theta. So this would be r cos theta. And this point here, which is +2 on the imaginary axis, is r sine theta. And we can say that tangent theta is equal to sine theta over cosine theta, right? And what we can do to make this applicable to our problem is to multiply by r over r, which doesn't change the problem, but now it allows us to use the values that we have in our diagram. So we can replace r sine theta in the numerator with 2 and the denominator -2. So essentially tangent theta equals -1. So if we do tangent inverse of -1, this equals our theta. And if you plug this into a calculator, we get -pi/4. Okay, so this is our theta. However, you'll notice that it actually isn't our theta. It's this angle that they're giving us, right? Because when we plug these things into our calculator, it doesn't give us every possible angle. It gives us the angle between, so for tangent, it'll give us the angle between -pi/2 and pi/2. So what we need to do is manipulate the answer that we get from our calculator. So we'll, instead of calling this theta, we'll have to call this theta prime now, right? And then we'll have to add pi units to it to get it to where we want it, right? So our theta should be -pi/4 pi. So this gives us 3pi/4, right? And so that gives us our theta. And now we need to find our r. And we can do this straight from Pythagorean theorem. This distance here is 2. This distance here is 2. And I'm using absolute value because I just want this distance absolute value, right? I want r as an absolute value. I don't care if it's negative or positive. So I can do r equals square root of 2 squared plus 2 squared, which is square root of 8, which is 2√2. So my polar coordinate then is going to be 2√2, comma 3pi/4. So this is my r comma theta, right? So I personally don't like looking at it this way here. I just like looking at, I like plotting my point, and I would have just found this angle alpha, right? That way I just have to deal with one triangle, but you have to remember that it's not alpha that you're looking for. You're looking at it with respect to this origin, right? So then you would have to do essentially pi minus alpha. Theta is equal to pi minus alpha to find the theta that you want, right? And I think this way is a little bit simpler. Then you would just do tangent of alpha equals opposite over adjacent leg, which is 2/2. This equals 1. Therefore, if we do tangent inverse of 1, we get pi/4, right? So we know that pi/4. So essentially, this is kind of the same thing, but now we don't have to deal with this projection and add pi, right? I think it's a little bit more, if there's a chance that you're going to have to manipulate the angles, why not just deal straight with the triangle? It's a little bit easier to see, and you know you've picked the triangle, so it's a little bit easier to deal with. So I personally like going with this route. So then theta here would be pi minus pi/4, which of course would still give you 3pi/4, right? So that would be the route that I would have taken, but it's completely up to you. Okay, so before we end this problem, we can also express this polar coordinate in terms of an exponential. Okay, so this is also equal to r e to the I theta. Okay, so we can write this as an exponential. And I'll explain where this comes from in a second. So R, we found R here. So if we were to write it in this equivalent form, it'd be 2 root 2 e to the I theta, which is 3 pi over 4, right? So this is equivalent to this polar coordinate notation, okay? So sometimes you might be given a problem in this exponential notation. Sometimes you could be given it in this way. So you're just going to have to learn how to get comfortable manipulating back and forth from Cartesian to this exponential form to the polar coordinate form. But essentially tells you the same thing. And again, as we've discussed up here, you might be given some alternate form. You might be given a negative r or a negative angle or some multiple of your angle. So be able to simplify that or find equivalent expressions. So get comfortable with doing that. So where does this come from? So r e I theta. So where this comes from is the Maclaurin series of e to the x, right? So Maclaurin series, let me write this above, let me write that first. So e to the x would be 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus dot, 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 right? So it starts from that. Yes, it is that, exactly. Euler's formula, but you can see this is where it's coming from, right? So if we replace, instead of, so we've learned to start with a known Maclaurin series, right? Core functions. You guys, some of you guys have done a project on this, and we know that we can multiply to it and manipulate the angles. Yeah. So you'll find this pretty neat. It's actually pretty. I've seen it for the first time not too long ago, so I was pretty impressed by it. So we can multiply this r out front in front of this whole series, right? So if we multiply the constant to this e to the x, we can do that, right? So I'll have this r out front, and now instead of x, I'm going to replace x with I theta, right? So 1 plus I theta squared over 2 factorial plus I theta cubed over 3 factorial plus I theta fourth over 4 factorial, right? So on and so forth. I'm going to write these out so you can see how I break them up. And now these are all sums, so I can group these terms, these individual terms, in whatever way I want, okay? In whichever order I want, as long as I account for all of them, right? So what I'm going to do is I'm going to group every other one together. So all the one in red, I'll group together. All the ones in green, I'll group together. So if I group the ones in red first, I'll have 1 plus I theta squared over 2 factorial plus I theta to the fourth over 4 factorial plus dot, dot, dot. And then, I need a bigger bracket there. And then the second grouping, plus, would be, and now I can factor out an I in front of this, all these terms of I in front of it, all the ones in green. So be theta plus, now, I squared theta cubed over 3 factorial plus I to the fourth theta to the fifth over 5 factorial plus, right? And now we use what we know about i's, right? So I is square root of -1, I squared would be negative 1. I cubed would be negative I. Oops. Let me be consistent with how I write my i's. I to the 4th, it would be back to 1, right? So this would be 1 minus 1 minus theta squared over 2 factorial plus theta 4th over 4 factorial plus dot dot dot, right? Because I took this I squared and made it minus 1, this I to the 4th and made it plus 1, as we've seen here, right? So that's my first grouping. My second grouping, I have theta. This I squared becomes minus 1 minus theta cubed over 3. This becomes plus 1, so plus theta to the 5th power over 5 factorial plus dot dot dot. And you can see that there would be a pattern for each of these. And if you look at your core functions from your book again, you'll notice that this is a definition of cosine for Maclaurin series. And this guy here is a definition of sine. So this is cosine theta, this is sine theta, Maclaurin series, okay? So this would be plus I sine theta. And as you can see, if we just distribute the r's, we have ri sine theta, right? Or let me put the I in front, R sine theta. And again, this is just going back to our form A plus BI, right? I wrote it as IB here, but this is B, this is A, and this is nothing but how we define, essentially, you know, it's like our Cartesian coordinate analog, right, on how we plug this. If we get rid of the I, it's essentially our Cartesian coordinate, right? So if we get rid of this I here, that's how we derive the Cartesian coordinate given our polar coordinate. And basically, this is equal to R e the I theta, right? So that's where this guy comes from. I know it doesn't look, it looks nothing like, it's like, how the heck does this turn into that, right? So, but that's essentially where it comes from. So any questions on that so far? Hope that wasn't too confusing. Okay. So now let's we can finally look at problem 1.2. But these are all similar. So we're going to express this in polar coordinates and as the exponential. So let's plot this point. So we're going negative root 3. So I imagine it's somewhere over here. We start from somewhere over there. And we want to find our angle, right? So I would be in the I direction, we have a unit value there. So let's just say that's 1, that's negative root 3. So this is my imaginary, this is my real, okay? So I'm looking at this point here. I'll get rid of this point, make it a hash mark. Okay, so now this is my R, right? So again, you can find the angle however you like, but I'm gonna opt to look at this triangle here. So that means this is my alpha, and this blue is the theta that I want. So I'm going to solve for alpha. So tangent of alpha is going to be opposite over adjacent, so 1 over root 3. And I choose positive. I'm just doing everything positive, okay? So that's one of the perks about just using the Pythagorean theorem and just looking at a right triangle. All you care about is this angle. It doesn't matter positive or negative. And then based on this graphical representation, you can figure out whether you need to add or subtract pi from it, right? So I'm going to keep everything positive. Therefore, tan inverse of 1 over root 3 is going to give me alpha, which this is equal to pi over 6. Okay, and therefore our theta is going to equal, so again, this is pi, so I need to go pi minus the alpha that I just found, right? That's what's going to give me theta. So pi minus alpha pi over 6 will give me 5 pi over 6. So that's my theta. My r, again, using Pythagorean theorem, will be the short leg, square root. Short leg is root 3 squared. So here it doesn't matter whether you take positive or negative, but again, since we're just dealing with this, isolating this triangle, we're keeping everything positive. And then that was the longer leg. The shorter leg is 1 squared. So this is 3 plus 1, 4. So my r is 2. So my polar coordinate would be 2, 5 pi over 6. So this is my r theta. And as the exponential term, it'd be 2 times e raised to the I theta 5 pi over 6. Okay. And just as a quick reference, I'm sure you guys have all this memorized, but in case you don't, whenever I deal with sines and cosines, I'm embarrassed to admit it, but I almost always have to write this table to derive all the angles. So it's always, just in case maybe some of you guys might find this beneficial, sine, I write sine, cosine, tangent, and I start from 0 and I increment all the way to 90, so pi over 2. So pi over 6 is 30, pi over 4 is 45, pi over 3 is 60, and then pi over 2 is 90, right? So 0, 30, 45, 60, 90. So this is how I always come up with it. And then it goes 0, 1, 2, 3, 1. And they're all divided by 2. Or the middle 3 are all divided by 2. And all of the numerators are going to get the square root in front of it. And of course, square root of 1 is just 1. So that just becomes 1/2. And then for cosine, all you're doing is the reverse order. So it starts from 1. It becomes root 3 over 2, root 2 over 2, 1/2, 0. And of course, tangent is sine over cosine. So 0, this is 1/2 times 2 over root 3, which equals 1 over root 3. Root 3 over 2 times 2 over 1 equals root 3. Sorry, that was the one below it. This is 1. This is root 3. And then this is undefined, right? Sine over cosine. So again, I personally I have to come up with this. For some reason, I've always had issues memorizing these, but some of you may not. But you might find this table useful for this section at least. So let's look at 1.3. 3 plus 3 root 3 I. Okay, so let's plot this point. This is my real axis and imaginary. So 3, so we'll say 1, 2, 3 is here, and then 1, 2, 3 plus some root 3 up here, right? So it's essentially this point here, right? So 3 and 3 root 3. My R is this point here. Okay, this is my theta. And now I can find this one directly, right? Because my right triangle is in the first quadrant. So I don't have to do any sort of manipulation. I can just look at that right triangle and come up with theta directly. So tangent inverse of root 3 times 3 over 3, which is essentially tangent inverse of root 3, tan inverse of root 3. And then we can just go to this table here, right? That is associated with pi over 3, which equals theta, right? So my r we can find by doing Pythagorean theorem. So this is 3 squared, not cubed. 3 squared plus 3 root 3 squared. So root 9 plus 27. So this is root 36, which equals 6. So my radius is 6. So in polar, this is 6 comma pi over 3. And as the exponential, this is 6 e, so r, e to the I theta, so 6 e I to the pi over 3, right? So again, one more problem. Or actually, no, that was the last one in that section. So yeah, I know it's getting pretty repetitive. Once you get it down, it's pretty simple. So now, let's try manipulating it a different way. Now we want to write these following problems in the form a plus bi. Okay, so we want to write it in that form. We're given e to the I pi. Okay, so how do we go from this exponential form to this form here? Okay, so recall it's in the form r e to the I theta. So we know r equals 1 and theta equals pi, right? So that's what we can get right away from that. So again, recall from the derivation up here, this guy here, right? So it's r times cosine theta plus I sine theta, right? So this equals r cosine theta plus I sine theta, right? So since we found r, this is 1 times cosine of pi plus I sine of pi, right? And we can do some simplifications. Sine of pi is 0. Cosine of pi is -1. Therefore, this is -1. So there's our answer, right? So we don't have any imaginary terms for this expression. Okay, so get the next one. 2. Let's say we had e to the pi minus I over 2. This is all in the exponent, all in the power. We can rewrite this expression as e to the pi times e to the negative I pi over 2. So that means this is my r, right? And this is my theta, actually with the negative sign, right? The negative sign is included in that. So if I rewrite this, r equals e to the pi, and theta equals negative pi over 2. Don't forget the negative. So now let's write this in this form here. So r is e to the pi, cosine of theta, negative pi over 2, plus I sine of negative pi over 2. Cosine of negative pi over 2 is 0. So we're left with, and then sine of negative pi over 2 is -1. So this is -1. So we'll have -1 e to the pi I. Or I'll just say negative e to the pi I. Okay, there's our answer there. Okay, so now 2.3 e raised to the I over 6. So my r equals 1, theta equals pi over 6. So this should equal 1 times cos pi over 6 plus I sine of pi over 6. Right. So yeah, this is where I have issues with cosines and sines. So that's why I always refer to this. So cosine of pi over 6 is root 3 over 2. Sine of pi over 6 is 1/2. Right? So this is where where the table comes in handy. So cosine of pi over 6 is root 3 over 2 plus I sine of pi over 6 is 1/2. So there's my equivalent answer. And then let's look at the last one for this section, 2.4. E to the pi over 2 minus I. So again, we can rewrite this as e to the pi over 2 times e to the minus I. And this is equal to, so this is my r. What is my angle? So my angle here is theta is -1. Okay? So e to the pi over 2 is my r times cosine of my theta, which is -1, plus I sine of theta, which is -1. I'll just leave it in this form. I'm not going to punch in -1. Sine and cosine of -1, they're weird numbers, so they're decimal numbers. So I'll just leave it as this is my final form. Okay. So any questions on this section so far? Okay. One. Okay, so we want to basically simplify the following expressions. Simplify expressions and write in the form A plus BI as we did in the previous example. Okay, so 3.1 is going to be 4 minus 3i minus 2 plus 5i. This is no different than regular addition and subtraction, right? So now we just have imaginary terms. So we're going to group the imaginary terms and then the real numbers separately, right? So this is essentially just 6 minus 8i, okay? So again, we're just treating, this is almost basically like addition and subtraction of real numbers, but we're grouping the imaginaries separately, right? So same with multiplication, right? So we multiply this out, we get 6 minus 8i plus 9i minus 12i squared. We know I squared is -1, so this becomes positive 12. So we'll add that to the 6, we get 18 plus I. So there's our simplified answer in terms of A plus BI. 3. Let's say we had 3 plus 2I over 2 minus I. So how can we simplify this guy? Well, we can always multiply by the conjugate when we have this scenario of the denominator, right? Because I want to get rid of this denominator and simplify. So I'm going to multiply by the conjugate, and I'll get 6 plus 3i plus 4i plus 2i squared. And then this becomes 4 minus I squared. So this I squared will make it -2. This would be 4 plus 7i. And in the denominator, that'll make it -1. So this is plus 5. So this would be 4/5 plus 7/5 I. Okay. Pretty straightforward here. 3.4. How about I to the 99th power? So earlier we looked at, I wrote these out, and we see in the pattern, this is negative I, right? So using this pattern, we can figure out what I to the 99 is without keeping track of each exponent. So essentially what we want to do is divide 4 into 99 and see what the remainder is, right? Because every 4, we get 1 back, right? So if we do this, we get 2, 1, 9, so 4, 16, 3. So 24, remainder 3. So this is equivalent to I cubed. Okay, so this is essentially this guy here, which is negative I. So there's my final answer. All right, pretty simple. Okay, this last problem somehow made it on this worksheet. It's very, very easy. I don't think you guys will have any problems with this, but since we have a few minutes, we'll go over it. So now we're just finding the roots, right? So you guys should already know how to do this. So now that we're dealing with imaginary numbers, we're able to take the square root of negative numbers. So, right, so this becomes, actually, I should have a plus or minus here, right? And then a minus inside of the square root. So it should be plus or minus root 5i, okay? 2. 2x squared minus 11x plus 14 equals 0. Basically, we're just going to use quadratic formula, negative b plus or minus b squared minus 4ac over 2a, right? So again, if this is less than 0, then we have imaginary, right? So this one actually won't, this won't have imaginary terms. 121 minus 4. This quantity up here becomes 9, positive 9. So positive. So this is just 11 plus or minus 3 over 4. 4.3. So of course, if we had a determinant, this is the determinant, where that's less than 0, we'll have imaginary numbers as we do in this case. So negative b plus or minus b squared minus 4 times a times c. This quantity is negative 16 over 2a. So this becomes negative 12 plus or minus 4i. So that'll take care of the negative square root of negative 1 over 16. So this gives us minus 3/4 plus or minus I over 4. Okay. So again, pretty straightforward. You guys should already know how to do that, but yeah, made it on the worksheet. Figured it'd be a good review. So again, that's all I have for today. Any questions for me on anything that we went over, or anything else in general? Okay. Yeah. So again, we're not going to meet on Wednesday. I'll post the